All right, so good afternoon, everyone. My name is Jesse, and I am with Exploring by the Seat of Your Pants. For those joining us for the first time, we are all about bringing conservation, adventure, and science into classrooms around the world. Right now, we're joined by 7 classes from across Canada, so I'm going to give them a chance to do a bit of a shout-out. We've got Miss Slaney's grade 4s in Calgary, Alberta. Hi, guys. Awesome. We've got Mr. Shorts, grade 4-5s in Kitchener, Ontario. Hi, guys. Hey, again, so the mics are muted, but that's okay. We appreciate the enthusiasm. We've got Mr. Richards, grade 5 through 8s in Amherst View, Ontario. Hi, guys. Awesome. Forget those mics working. We've got Mr. Chitaro's grade 9s in Windsor, Ontario. Hey, guys. Awesome. There we go. And then we've got Mr. Tilston's grade 12s in Espanola, Ontario. Hi, guys. Wow, so rare that we have grade 12s. I love it. We've got Miss Spears, grade 4 through 7s in Moberly Lake, BC. Hi, guys. And last but not least, again, the mics just aren't working right now. We'll get them working by the end. We've got Miss Hills, grade 4s in Burlington, Ontario. Hi, guys. Awesome. Of course, the reason you guys are all here today is for our speaker. So we are joined live by Dr. Erica Caden for the second time in the Sudbury Neutrino Observatory Laboratory, or Snolab. So there they study the mysteries and the history of the universe in a mine, in an advanced research lab 2 kilometers under the ground. So why on earth do they do that? Well, Dr. Caden's going to tell us a little bit about her own work and about the work they do at Snolab. And so without further ado, Erica, you'll have to demute your own mic, but after you do that, you can take it away.
Hi, Jesse. Thank you for the introduction.
Yeah.
Everyone can hear me?
Yeah.
Fantastic. So, yes, as you said, I work at Snolab. Shout out to the class from Espanola, Ontario, just down the road a piece. I am going to, I have a little bit of a presentation that I'm going to give you guys and then kind of walk you around the control room where my experiment is and then answer your questions. So let's get to share. All right, are we good?
You're good.
Fantastic. So this is me doing science underground. So I'm a research scientist at Snolab, and Snolab is an astroparticle physics facility in Sudbury, Ontario. So you can see where the little purple pin is in the map. That's where we are. We study astroparticle physics from deep underground, 2 kilometers at the bottom of, almost at the bottom of the number 9 shaft in Creighton mine, which is an active nickel mine. They're actively mining nickel and copper ore from this red ore body. So this is actually in an active mine. It's the perfect place to do deep underground science, and I can tell you why. We are 3.5 times deeper than the tallest structure in the Western Hemisphere. So you can see relative scale. There's the CN Tower. So this ore body is full of nickel and copper, and it keeps going down. But we just stop at the 6,800 level and then walk another 1.5 kilometers underground to get to our underground facility. So that brings us then to Snolab. So we study, as I said, astroparticle physics underground. The facility, I like to describe it as like a shopping mall. It's 5,000 square meters in area, or 54,000 square feet. And so we have different drifts and tunnels that we can house smaller experiments and large caverns to hold the bigger experiments. And this is the experiment that I work on currently, called SNO+. So at Snolab, we study neutrinos and dark matter. So these are fundamental particles. I mean, they're little plushies here, but for us, they're particles. They are fundamental, neutrinos are fundamental particles. They're similar to electrons, but they are very hard to detect. They are produced in radioactive reactions like fusion in the sun or fission in nuclear reactors, or regular normal particle decays. We get neutrinos coming out as well, but they are different from electrons in other ways. They don't have any charge, and there's a couple of other big differences about neutrinos than electrons. But we can use neutrinos to help us answer questions about the world around us. Like, why is the Earth so warm? How do elements in the sun form? How do stars explode? How are we even here at all? Neutrinos can help us answer those questions. So this is another picture of the experiment I work on. This is called SNO+. It was originally the SNO experiment that helped confirm some properties of neutrinos by studying the sun. And for that, the leader of the experiment was a co-winner of the Nobel Prize in Physics in 2015. So now we've upgraded some of the hardware and are looking for neutrinos and different energies and from different reactions. So you can see our little neutrinos follow us around everywhere. And this is an actual photograph of the detector from waterproof cameras that we have mounted inside. So this is what it looks like from inside. The cavern that the detector was in is 21 meters wide, and this outside, the outside of the detector where all the little dots were, is 18 meters, and the center part is 12 meters in diameter. So this is a really massive structure. This inside is filled with water. So each of these dots that you see is a light sensor that detects these tiny flashes of light that happen when the neutrinos interact. And we can count up these flashes of light and determine how much energy the event had, and determine if it was a neutrino or something else that happened inside our detector. These lines are ropes that hold the detector up or down as it's filled with different materials. Some are more buoyant than water, some are less. And everything is flooded with water. It's in a big pool right now, but the center part will be filled with mineral oil soon. And so we can expand our science capabilities with different materials. So that's the main neutrino experiment that I work on. But at Snolab, we also study dark matter. So dark matter is, we like to call it the invisible space glue that keeps galaxies and galaxy clusters from spinning apart. So dark matter is what holds it all together. But we haven't actually observed a dark matter particle yet. We're still looking for it, which is one of the exciting things about doing new research in science, is that we don't know everything yet. We're still looking for the answers. It's keeping us on our toes. So these are just some of the experiments we have at Snolab. There's also some projects studying fruit flies and biology, as well as other neutrino and dark matter experiments. So I am... So let me show you around a little bit. Here is the control room behind me. We are going to, so people are here working on different things. There's people who are working on a process plant for purifying liquids, and there's people working on the detector right now. They were doing some electronics work. So we're going to quickly walk out on deck. Here is one of the photosensors that I had talked about. They are pretty big and they are very, very sensitive. You can detect tiny, tiny flashes of light with them. If there was a candle on the moon and you had one of those on the surface of the Earth and everything was completely dark, you could see the candle on the moon. They're incredibly sensitive light detectors. And so here is the deck clean room, or I'm sorry, this is just the deck of the detector. So there's, I can't walk too much farther out, but this is, we would be on top of the detector, which is underneath us in the water from right here. You can maybe see some of the flashing lights back there of the electronics, maybe not quite. This is what Snolab is. It's a bunch of hallways and caverns holding different science experiments that are trying to understand the world around us.
Very cool. So with that, unless there's something else you wanted to show us right off the bat, we could go to questions and then just flesh out all the things that you've discussed already. Does that work?
Yep.
Awesome. All right. So let's go to Miss Slaney's group. If you guys have any questions to kick us off, go right ahead. Yep, you're good.
Okay. Why did you start this project? How long does it take to get from the top to the bottom? Like, how many hours or minutes or whatever?
Cool.
So this project has been working. There are about 150, maybe 125 people working on my one project on SNO Plus. There are many different aspects, and we need a lot of people with a lot of different skills. People who know chemistry, people who know engineering, people who know physics, people who know computer code. So a lot of people have been working on it for the last 10 years, I'd say, in upgrading the hardware to where we are now. So it's a long-term investment for a lot of people. So to get through the cavern is you have to do so in this little chair, and they hook you up to a winch, and that's driven by an electric drill, and you go down, and that takes maybe 5 minutes. But to go underground from surface, it's an active mine, so the mining company helps us helps maintain all of that equipment. So we just use it, and if we're going full speed straight down to 6,800 feet, it's 3.5 minutes, 40 kilometers an hour. The elevator goes.
Whoa.
Yeah.
That is a crazy fast elevator. And then, sorry, you need to walk the additional 1.5 kilometers once you get down there, correct? Yeah.
And you walk it, yes. It's good exercise.
And when do you come in the morning? Like, I'm sure there's not too many tours down or like groups that go down every day. So when do you come?
So today I got to sleep in a bit, and I just had to be ready at 8 o'clock in the morning, fully dressed in all of my mine safety gear. But most people start their day at 6 o'clock in the morning is when the cage leaves. So you have to be here and ready and dressed at 6 a.m. And you have to go down until 4 p.m. It's long days.
Yeah. Wow. So before we go to our second question, I just should note, because the mics are being a little wonky, every other class, only Miss Slaney's class can do. So we're going to Mr. Short's next. And if Mr. Short's class could demute their mic, that would be great. And then we'll go from there. So yeah, just top of your screen, little microphone symbol, guys. So everyone will be able to do this, and I'll prompt you one by one. But yep, you're good now.
I have a question.
Yeah, go for it.
You said there was something that I forget what it was, but there was something that explained how we came to be. Could you please go deeper into that?
Cool.
I will do my best. So after the Big Bang, we know that we would think that there should be equal parts of matter and antimatter. But we know that there's not, because we live in a world made of matter. So that means that there are some particle reactions that favor matter over antimatter. And that isn't necessarily how we would think that things would work. We would think that things would favor matter and antimatter equally. But we know that there's some reactions that favor matter over antimatter, but we don't know about enough of them yet to explain why we live in a matter-dominated universe. So we're looking at neutrinos and how they favor matter over antimatter to see if that can explain how we live in a matter-dominated universe. So I work on one neutrino experiment. I work on two. There's two at the lab. There's probably one more coming, and there are maybe between 50 and 100 different neutrino experiments all around the world looking at different neutrino properties. It's a small area of particle physics that is growing. So some of these are looking to measure how much neutrino reactions favor matter over antimatter? That's a great question.
It is a great question. It's a very difficult question to answer. That was a really admirable chance. That's something that, like, students, you guys will be learning in late level university. So it's hard to convey really easily. Just a quick follow-up. So what happens if matter and antimatter hit each other? What happens?
Energy, explosion, light, and then there's nothing. They annihilate, and then there's just light.
Very
and
cool.
Energy, yeah.
All right, let's head to Mr. Richards' class. Again, if you guys could demute your mic, come on up. And I'll let you know when you've got it.
There you go.
How do you find dark matter?
Well, we haven't done it yet. We search for dark matter by looking for the same as neutrinos, tiny flashes of light or tiny bubbles inside a detector. And if you have a very clean detector that doesn't have any contaminations and you put it deep underground so you don't have any backgrounds from the surface coming down, and you're very, very lucky and you have designed everything exactly for what the dark matter particle, how it would like to react in your detector. And then you can see these tiny flashes of light and say that you found something. So that's almost how all particle experiments work, is looking for tiny tracks through a detector or tiny flashes of light.
Okay, and for other students, could you explain a little bit about what it's hard to explain what dark matter is, but how much dark matter there is and why it's so important to find it.
Yeah, definitely. So what we see in the universe, everything that we can see, planets, t-shirts, stars, trees, all of that is 5% of what the universe is made out of. All of that is just 5%. About 25, 28% is dark matter. It is stuff that holds together, that interacts with gravity, and it kind of holds together galaxies that they're spinning and galaxy clusters as they're moving through space, but it doesn't react with light. It doesn't emit light. It doesn't give off light. So we call it dark because that means we can't see it. But we know it's there because galaxies would fly apart as they're spinning if we didn't have it.
Very cool. So this is something that makes up 5 times more mass in the universe than all the stuff we can see.
Everything we can see. You look in the night sky, you see the stars, and they're huge. They're much bigger than our sun, and we're nothing compared to how much dark matter there is.
Super cool. All right, let's head to Mr. Chitaro's class. If you guys have a question, come on up. Just, yeah, demute your mic. I don't know if you caught that when the students are coming in, but just microphone symbol, top of your screen. I'll let you know.
Yeah, we were just kind of getting settled, so we're just trying to catch up with all this science talk here. Anybody got something off the top of your head? We'll pass.
Well, okay, we'll come back to you guys in a minute. No worries. Awesome. All right, let's go to Mr. Tilston's class. Do you guys have a question? Go for it.
Can you hear us?
Yep, we're good.
I have one question off the floor. What's the force of dark matter?
What's the force of it?
Yeah.
Yeah. Oh, Erica, you're muted still. There you go.
So we think in physics that all of our understanding is there are 4 fundamental forces. We think that dark matter will interact via what's called the weak force. So this makes it very difficult to detect. It is much smaller in magnitude than the strong force. That's the most physics answer to your question, that it interacts via the weak force, which is what makes it so hard to detect.
And gravity too, though, right? It does.
Gravity, yes.
Yes.
Yeah. Thank you.
All right, let's head to Mrs. Spears' group. You guys have a question? Come on up. Yeah, so Mrs. Spears' class, you just need to demute that mic. Sorry, guys. I wish I could do this all for you. I usually can. Hi. But yeah, let's ask a question. Better than waving, I find.
Sorry,
there you go. You're good.
Can you hear us?
Yep.
Okay, sorry, we're just a little delayed because we're watching on YouTube.
Okay, that's fine.
Why do we study underground?
Why do we study underground?
Yes.
Yeah.
So so I said that all of our particle detectors are looking for tiny flashes of light. So part of that is that everything needs to be really dark, but it's not just dark to our eyes, it's dark to radioactivity as well. So particles come crashing through the sky all the time in our atmosphere, and it doesn't cause any problems for us, but they would make a lot of electrical noise inside our detectors. So we want to stop all those particles, and that's why we're 2 kilometers underground, or 6,800 feet. And that stops all of those other particles, almost all of them, from interacting in our detector. So it makes it a very quiet environment for that kind of background.
It's like if you were trying to look at a candle light when someone was blasting like 100 flashlights at you. It'd be very hard to see the candle. So if you go into the ground, you turn off the flashlights and you can look for the candle.
Exactly.
Sort of and so briefly, I want to go back to that point because I love explaining that to kids. So neutrinos, when you're standing right now, when you're out in public, you're standing above the ground, what's happening? How many neutrinos are hitting you?
If you hold out your thumb and you look at your thumbnail, you have 100 million neutrinos from the sun going through your thumbnail every second. So neutrinos are the most abundant particle other than light in the universe, but they don't interact. Maybe once in your lifetime, a neutrino will interact in your body. They just pass right through you, which is why it's great that they will pass through the 2 kilometers of Earth and interact in our detector. They're not stopped by the same rock that stops all of the other background particles.
Super neat. All right, let's head to Miss Hill's class. If you guys have a question.
Okay, guys, say hi. All right, Mateo and Tessa.
What's your favorite aspect of your job?
Remember, you're looking right here.
My favorite aspect of my job. I love learning new things. One of the best things about doing research in areas like asking the big questions that we still don't know the answer to is all of the little things that you learn in solving the problems as you go along. That's one thing that I like. Another thing is talking to classrooms like you guys. I love telling people about why science is so cool and why I do it and why you could do it too.
Well, we're happy to provide the opportunity. So I just want to note before we do our second round of questions, there's a few groups watching on YouTube Live. If you guys want to write your questions in the chat bar, I will pass them on to Dr. Caden. So please do that if you're interested. But yeah, let's go back through one more round, and we'll start with Miss Slaney's class.
What's the most fascinating thing?
What's the most fascinating thing you guys find? Is that the question? Good question. All right.
So I think the finding out the original experiment that mine is based off of found out some really interesting things about these particles, neutrinos. They are different from any other particles that we know in the universe, in that they change what kind they are as they travel through space. So a neutrino that is created in the sun looks different. It has changed fundamentally how it interacts in detectors by the time it gets to Earth. So this is, other particles do it a little bit, but not nearly as much as neutrinos do. You can't even say that a neutrino has a certain weight or has a certain mass if it's one type or one flavor. That we have 3 different flavors of neutrinos, and they can change one into another as they travel through space. So that is what the groups won the Nobel Prize for in 2015. And it fundamentally changed how we think of neutrinos. They were just this little tiny mathematical correction to all of the rest of particle physics that we understood really well. But neutrinos don't follow any of the rules. They are like the black sheep of the family. There's still so many questions, which make them so exciting because there's so much more to know.
Neutrinos, the bad boys of the particle world. I like it. All right, let's head to Mr. Short's class again for a second question. Come on up, guys. I like the mobbing around the computer.
Okay. Amaris. So,
Why did you guys choose the mines to do the experiment?
So that's a good question. We, the original SNO experiment chose this mine because we're right next to a university, Laurentian University in Sudbury. Also, the mine was very willing to work with the scientists. That it was owned by a local company, and they were really interested in supporting the science and supporting the research. And we could go deep. They had, we have the 2 kilometers of really stable rock above us. So that made it safe to dig down this deep. And they had already been doing mining. So we could just, everyone goes off in one way and we turn the other side to get to our area. So it provided the right, all of the right conditions to be able to do the research we wanted to do here.
Nice. Saves you picking up a giant shovel instead of a giant wrench to start digging when I get to the mine. So. All right, let's head to Mr. Richards' group. You guys have a second question? Go for it.
Okay.
how is dark matter formed?
So that's a good question. So we think it's, again, a fundamental particle, like most of the other particles we see, and that it has been around, again, since the beginning with all of the other particles. It's dark matter is the big mystery because we can see its effects. Like, you can see how it holds things together, and you can see the traces and how it bends light, but we haven't seen it. We haven't seen the dark matter particle yet. So all of the questions that we still have about particles, we normally answer them by smashing them into things or smashing or looking at their tracks. And we can't do that yet with dark matter because we haven't seen it yet. So there are a lot of ideas, and there's a lot of, well, if it does this, it has to have these properties. But it's an almost bigger mystery than all of our questions about neutrinos because we haven't been able to study it yet.
Super cool. All right. Let's head to Mr. Tataro's class. You can ask 2 questions too. So if you guys have 2 questions, you're welcome to ask them. And yeah.
You on the screen there. You see where, there you go.
You're good.
Hey, I'm Christian, and in this geography class, we learned about the Earth's crust. And the deeper you go, it's warmer, right? So I'm just wondering what the temperature would be at 68,000 feet.
6,800.
Yeah.
Yeah. So in the just mined rock, it's about 40 degrees Celsius. It does get hotter and hotter as we go through the Earth, as we go deeper into the Earth. And that's actually, I'm going to go on a bit of a tangent here. Part of that is because of neutrinos. So we know that the elements in the rock decay and they produce heat. We know that the Earth is warmer than it should be, than you would expect from just the sun's radiation coming down. So one of the ways that we hope to understand why it's that warm is by studying the neutrinos that are given off in those radioactive decays in the rock. So if we can count the neutrinos that we know are coming from the rock, we can estimate how much heat is produced in those reactions and to see if that matches how hot we're able to measure the Earth. We can study neutrinos that come from much deeper down in the Earth than we are able to drill. So we can use neutrinos to study the stars and to study the Earth.
Super cool. All right, let's head back to Mr. Tataro's class if you guys have a second question. And good question. And if you don't, that's okay too. But let us know. And we can come back in a minute, and we will. All right, let's go to Mr. Tilston's class for second question. Go right ahead, guys.
Can you hear us?
Nope.
Okay, so you said that we know about 5% of the mass in the universe, and we know about 25% of it is dark matter, but what's the rest of it?
Good question.
So the rest of it is dark energy. So that is the force that is that universe is expanding. So that is also another different big unknown in the universe. That is not something that we study here at Snolab, but there are other big experiments around the world that do study dark energy. So that's our whole pie chart of the universe is dark energy, dark matter, and normal matter.
Is there, I'm not sure if there is a way to explain dark energy really readily, but basically we know that there's this much of it because the universe is expanding the way it is? Is that the idea? Okay.
Yes.
It's tough. Again, this is one of those things you learn at late level university. So the fact that we're discussing it now is great, and hopefully you guys are catching most of it. All right, let's go to Miss Spears' class. You guys have a second. Oh, and Miss Spears is watching on YouTube, so hopefully they can hear this, and I'll make chit chat while they hopefully hear and get ready. There we go. Hey, someone heard. Come on up, guys. No hurry, all good. That's funny.
All right. Do you want to ask your question? Would you like to ask your question?
Sure.
Okay, go ahead.
Okay, what was it again?
Hannah's curious if they're worried because she knows something about the universe expanding. So she's wondering if they're worried about it expanding.
No, the universe expanding is not something that we are currently concerned about. It has been expanding and will keep expanding. It is not something on the level that you guys have to worry about, or that anyone has to worry about here.
All right, big sigh of relief. No, no Earth ripping apart and universe expansion. That's good. All right, let's wrap up with one last question from Miss Hill's class. If you guys want to end us off, that would be great. And I'll let you know. There you go. You're good.
Okay, Tessa, hi. Hi. Tessa, look here.
Yep, you're good.
What functions or parts of the mind help you to conduct your research in the SNO lab?
That's a great question. So the mind is very supportive of the science that we're doing. So they are the ones who run the elevator to help us come up and down, and they help anytime there's an issue with water flow through the mine, or the electricity that comes, the electrical cables that come through the mine. If we have engineering or structural questions, we can use some of their expertise and some of their contractors to make sure that all of the big caverns that we excavate are safe. Inside the walls, you can see the walls behind me are really rough. They have a spray-on concrete sprayed on them to help stabilize the rock that they took out. And there's also big 10-meter bolts that go through the rock to hold everything steady so that it doesn't fall apart. So that everything that we took, the rock that we took out that would normally support things, the bolts help keep things there instead. And the mine is also, they're also a big advocate for getting science done and for helping us talk to the public and the private sectors about why what we do is so important and why we should be able to stay here and keep doing science. That's a great question. Thank you.
It's a great question. One last thing I wanted to just go back to. You mentioned a clean room at the beginning. Could you explain to students what that is and why it's so important? So a mine is very dirty. It's dusty. You picture like Snow White and the Seven Dwarfs, how they come out and everyone's filthy because you're underground. You're in dirt. But that dirt would destroy our experiments because it's filled with little bits of rock. And like I was saying before, little bits of rock undergo radioactive decays, and those would create the same little bits of light in our experiment that we're looking to detect when we're looking for particles. So we're in a clean lab, which means that we have to shower every day. I come underground and I take a shower to wash off any of the mine dust off of my skin and off of my hair. I have to wear a hairnet, like you see, to keep any of my hair from falling off. Any materials that come into the lab have to be washed. They have to be cleaned and scrubbed to make sure there's no dust or dirt on them.
The floors are washed, the walls are washed, everything is washed. Even our little stuffies were vacuumed to come underground today to show you guys. And in addition, all of the materials that our experiments are made up of have to be, make sure that it's clean material, that there's no radioactivity in the materials themselves that would cause a false signal in our detector. So everything has to be cleaned. I'm not wearing gloves now, but if I go into that other cleaner area, then I have to put gloves on. And I even have to put on cleaner shoes that haven't been walking around on our very clean floors. Everything has to be even more clean in different areas of the lab.
Very cool. So I did lie. We did have a quick question sent in online, so I want to pass that to you. Two-part question. So how long did it take to build Snolab? And then the group noticed, so Miss Oliver's group noticed that the storage globe is covered in triangle shapes. Is there any reason why that is or what those are for?
The
I guess the here. Yeah.
Okay. So the lab took, it was, I don't think, maybe 5 or 6 years, I don't know that number offhand, to expand from the original area that was here. Let me show again the screen to see the. So
there you go.
This here, I will dig into this. So this was the original area of the lab just here for the original experiment. And then they finished all of this area. So the 2 other big halls and all of the other lab space, that took a number of years to expand and to finish. So to do with the excavation, the dynamite blasting, to clean everything out, to secure the rock, and to finish and smooth the walls and really make it open and a clean space. So years and years of time and investment from different, from the government and from different contractors on finishing the space for us. So now you said the triangles, these?
Yeah, that's perfect.
So this is the back of the detector. So this is the outside before we, I think this picture was taken during the original construction of what was the original SNO experiment. So these metal pieces of steel are the supports that hold these panels of plastic, and each dot is one of those photosensors that I talked about. So this is the technical term would be a geodesic structure, but it's the best way to support a sphere without using straight lines. So these hold all of the steel pieces, hold all of the plastic pieces together. Plastic pieces hold the light sensors, and all of that is the outside, the back of the structure. And the inside here, you can't see the steel pieces, but you can see the front side of each of those dots. Every bright spot here is one of the photosensors, and on the back side, you would see the back of it.
Great. Thank you so much, Dr. Caden. So as we wrap up and as you come out of screen share, I just want to note for classes too, if you guys have any other students that are interested, not only does Snolab have a really robust online education platform where you can learn more, but we'll also be doing another hangout with them in early February as part of our entire month dedicated to highlighting amazing women in science. And so Dr. Caden will be back with us then, which is great. So what we do at the end of every hangout, guys, and I'm going to need you guys to demute your mics all together here. So boys and girls, please get ready. I'd love if you join me in saying a huge thank you to Dr. Caden for joining us today. So again, yeah, demute away and go for it.
Is anything?
Thanks so much, guys. Great questions from everyone. We look forward to having you back soon. Dr. Caden, that was great. Thanks so much for showing us around Snolab and telling us all about what you do.
Thank you. Hope to do it again soon.
Awesome.